Imagine any point inside a structural material, like a steel beam. That point is experiencing forces pulling and pushing on it from all directions. We can represent this complex state of force with a simple idea, stress. For a flat object, a condition called plane stress, we only need to consider the stresses in a 2D plane. A normal stress, sigma x, pulling horizontally, another normal stress, sigma y, pulling vertically, and a shear stress, tau xy, trying to distort the square. Now, if we know these x and y stresses, that's great. But what if the material has a weak spot along an inclined plane, like a weld? The stresses acting directly on that plane might be much higher. So the critical question is, how do we calculate the normal and shear stress on any arbitrary inclined plane? To solve this, we can use a classic engineering trick. Let's zoom in and isolate an infinitesimally small wedge of the material right along that cut. The fundamental idea here is equilibrium. This tiny piece isn't flying off into space, so all the forces acting on it must perfectly balance out. We know the stresses on the vertical and horizontal faces. Our goal is to find the new normal stress, sigma x prime, and the new shear stress, tau x prime y prime, acting on this inclined face. To balance forces, we first need to convert these stresses into actual forces. Remember, force is simply stress multiplied by the area it acts on. If we define the area of the vertical face as delta A, then simple trigonometry tells us the area of the bottom face is delta A times tangent theta, and the area of the inclined face is delta A times secant theta. Now for the core of the physics. The sum of forces in the x prime direction must be zero. We have the force from sigma x prime on the inclined plane, and then we add the components of the forces from the other two faces that act along the x prime axis. Writing this all out gives us a rather intimidating equation, but notice the area term delta A is in every single part of the expression. This means it cancels out completely. The relationship depends only on the initial stresses and the angle. After a bit more algebra, like replacing tangent with sine over cosine, the equation cleans up beautifully into this form. This gives us sigma x prime in terms of our original stresses. We can do the exact same force balancing act in the y prime direction. The process is identical, and it gives us this corresponding equation for the new shear stress, tau x prime y prime. Now, these equations are correct, but we can make them even more elegant and useful. The key is to use these double angle identities from trigonometry to replace the squared terms and products of sine and cosine. When we substitute these identities into our normal stress equation and regroup the terms, we get this result. This is the first of our two final transformation equations. Notice how it's now in terms of 2 theta. And we do the same for the shear stress equation. The substitution gives us this much cleaner second equation. Together, these are the general plane stress transformation equations. Crucially, these equations are meaningless without a consistent sign convention. First, for normal stress, tension is positive and compression is negative. For shear stress, we define positive shear as that which tends to rotate the element counterclockwise. Finally, the angle theta is measured from the positive x-axis. A counterclockwise rotation is a positive angle, and a clockwise rotation is a negative angle. If you stick to these rules, the transformation equations will always work. So there you have it. By starting with a simple concept, a tiny wedge in equilibrium, and applying some trigonometry, we derive these powerful transformation equations. They allow us to take a known stress state in one orientation and find the precise normal and shear stresses on any other plane inside the material.